All right. So today I just want to update you guys with the situation of us using our simple bug Mesoplasma florum to try to get an understanding of the design principle of how membrane lipidome actually adapt to temperature. So as Katerina already mentioned earlier in her talk, the membrane is essential for life and it is a biophysical construct. So it has to have some critical biophysical properties like mechanically robust and also it has to be fluid so it maintained biologically active. And to perfect this material, life has selected lipids. The thing is, like all other material, lipid membrane actually change biophysical properties, in this case, membrane fluidity with temperature. So if you just have a membrane and then you put it at higher temperature, membrane fluidity will decrease, which create a less robust membrane for an organism, which is less ideal. So biological membrane actually try to maintain their membrane fluidity at a certain level. And the way they do it is actually changing the composition of their membrane lipidome when they go from temperature to temperature. So this mechanism is an universal phenomenon and is also available in Mesoplasma florum. And last year in the fourth JCVI workshop, we see that Mesoplasma florum can actually perform this homoviscous adaptation across a pretty wide range of temperature from 15 to 38 degree. And at that time, we were using FBS serum to feed it, so it has quite a lot of lipid. And this is the same case for most organisms that people have witnessed homoviscous adaptation in, is that they use a lot of lipid to do it. So where does this lipidomic diversity came from? So in Mesoplasma florum membrane, you have kind of two parts. You have the phospholipid and you have the cholesterol. The phospholipid can be complicated because it has different azo chain, it have different head group, and then the sterile part actually for Mesoplasma florum, you can change it. So, and because we actually control the lipid we feed the bacteria, we can control the lipidome diversity. So hence our question, how does changing the lipidome diversity can actually affect the adaptation to different temperature? So in this presentation, I will feed the bacteria with diets with varying in the diversity of azo chain, head group, and also cholesterol. So first, how azo diversity changes homoviscous adaptation. And here you have two diets, one with 2 fatty acid and cholesterol, and one with 4 fatty acid and cholesterol. For the 2 fatty acid, you have a shorter azo chain, which is saturated, so no double bond. And then you have a longer azo chain with a double bond. And for 4 fatty acid, you have the combinatory long and short saturated and also long and short unsaturated. And if you look at how the membrane fluidity is being maintained, you can see that they do drop a little bit. So having only cholesterol and fatty acid chain actually hinders the homoviscous adaptation. But the trend does not really change if you add 2 more fatty acid comparing to the simplified one. And the lipidome can also be classified by lipid class. In this case, they have cholesterol that we feed them. And from the fatty acid, they make PG and DAC. And the pattern for class adaptation looks the same. However, if we look at how they actually arrange the azo chain, we see something pretty interesting. So if you feed them 4 fatty acid, you can see a pretty canonical remodeling in the case of at higher temperature, they choose to make phospholipid with longer chain length and fewer double bond. But in the case of a restricted diet with only 2 fatty acid, the double bond is already coupled with the chain length, so they are forced to choose. And in this case, we see that they choose to adapt to the double bond pattern. So the average double bond for diet with 4 fatty acid and 2 fatty acid are similar, and they completely forego the adaptation with azo chain length. And if you remember from the previous slide, the adaptation pattern is similar across the two of them, meaning double bond adaptation is more important for homoviscous adaptation comparing to a chain length adaptation. So this is a pretty restricted diet, and we can easily introduce more diversity to it by adding another phospholipid. In this case, sphingomyelin is something that they actually also take up from the serum. So if you look at how they homoviscously adapt, we see a pretty impressive recovery because they are able to maintain membrane fluidity much better, and also they actually gain 4 more degree of viable temperature range. Furthermore, if you look at lipid class abundance, you can see that the sphingomyelin that we use to feed them, they actively enrich sphingomyelin abundance at higher temperature. So even if we feed it a lipid, Mesoplasma florum knows which one to enrich. And as like a small bonus, you can see that the abundance of cholesterol drops significantly comparing to the diet with only fatty acid. And we are hypothesizing that this might be the reason why they actually earn another 4 degree in a viable range, because they don't have to push cholesterol abundance that much higher. However, if you look at how they remodel PG, so the main phospholipid that they actually make themselves, we see that the pattern changed completely from 2 fatty acid and 2 fatty acid with sphingomyelin. So this signifies to us that the dynamic of how this bacteria homoviscously adapt changes significantly with the presence of a new lipid class, and in this case, which is sphingomyelin, which pops up a new question. All organisms have different sets of lipid with different head groups. So how does that came to be? And that is partially answered with our next experiment, where we feed the bacteria fatty acids, sphingomyelin, but we switch out cholesterol to a bacterial sterol analog called diplopterol. What you're looking at here is the lipid class abundance when we are feeding it the 2 fatty acids, sphingomyelin, with either cholesterol and diplopterol. And you can see from the left, the green bars, that cholesterol and diplopterol abundance is relatively similar. However, in diet with diplopterol, PG level plummets. So PG is the only, or like the most abundant phospholipid that they actually make. But if you feed it diplopterol, the membrane, instead of incorporating PG, actually incorporates sphingomyelin. And why could this be? We hypothesize that the reason this phenomenon happened is because PG actually in Mesoplasma florum frequently have the unsaturated bond. And this unsaturated bond is at delta 9, which we found in previous publication that that unsaturation at delta 9 does not have a favorable lipid-lipid interaction with PG. This is not the case for sphingomyelin. We also look into how diplopterol interact with sphingomyelin, and they actually have favorable interaction. So our new hypothesis is that lipidome head group diversity actually have to be accounted in the context of the biophysical constraint grounded with lipid-lipid interaction. So with that, the take-home message from my talk would be that florum is a powerful model organism for lipid studies, and with this organism we already uncovered a few patterns for homoviscous adaptation. In case of azo chain, we see that double bond is prioritized over chain length, and having different head group diversity has great effect on how the lipidome is being remodeled. But all of that lipidome remodeling has to exist within the constraint of the biophysical lipid-lipid interaction. So with that, I would like to conclude my talk, and I hope I keep you entertained.
Thank you, An. A quick question. So with Mesoplasma, is the selection of is the selection of one lipid over another, is this a passive process or an active process?
So we do have data from FBS where they have a selection of PCP, sphingomyelin PE. So they have a plethora of phospholipid class to select, and they pretty much selectively pick sphingomyelin, and actually picking sphingomyelin by a way higher fold over PC. This is pretty rare because in terms of head group chemistry, they are relatively similar. So it seems like they do have selectivity in that regards.
How would they do that?
So we have not found the enzyme or like any protein that binds lipid in this case yet. So unfortunately, we don't know. But yes, this is something interesting because, for example, we see that for mycoides and SYN3, even though they are related, they take up way more PC compared to sphingomyelin. So it seems like Mesoplasma has some selectivity in that regards.
And so, whereas if you were to do the same experiment with, like, just putting synthetic vesicles into a solution that had these different lipids in solution, you wouldn't get passive incorporation of specific lipids into the vesicle.
I don't think that would be the case, no, especially if when you see this data when we switch out cholesterol and diplopterol, the fact that the main lipid that they synthesize, which is PG, completely plummets, and instead they take up sphingomyelin, really speaks to that this is not a passive process. And there is selectivity there that is also grounded by how lipid interact with one another as well.
If you were to put the dilopterol into a JCDI SYN3B culture medium, does it take that up?
So they do take it up, at least for mycoides. I definitely try that. The only thing is that I was trying to titrate out cholesterol to replace it with diplopterol. And at some point when the concentration of that cholesterol is very low, they're still alive. But when I take them all out, then they are dead. So we think that they need some trace amount of cholesterol to be able to live. So that's why Mesoplasma is good.
And Shlomo Rotem and Shul Razin, I think, showed in the 80s that they could gradually wean mycoides and capricolum of cholesterol and develop really wimpy cells that I think they published that there was none, but I could be wrong about that.
No, that was published, and that actually was the inspiration when I first going into mycoides, but I was trying and I really couldn't reproduce that data.
Okay, and again, so I guess they would have had to have done that without serum unless they or because it doesn't seem like there would be cholesterol in well, who knows what's in mycoplasma broth base
No,
broth.
yes, the broth base could be the case, or a lot of work was using BSA, and BSA needs to be completely delipid. BSA always hold on to some lipid, so if you don't delipidate it completely, there could be trace amount left.
Thank you very much, Anna. I really appreciate your doing, and thank you for giving a terrific talk to finish us up this year.